So again, if you're not interested in learning more about the multiple maximum likelihood estimation approach that's used for estimating the parameters in a logistic regression model, you can skip this video. If you are interested, I'm just going to walk you through one example of this using our Donner data. So recall that we're trying to estimate, I called it pi here, but P, we're estimating the probability of survival in this data set. So pi is equal to probability that y equals 1, or probability of survival in this case. Okay. And in logistic regression, we basically assume that, so y takes on the values either 0 or 1. Okay. Each y, person either survives or dies, so each y is either 0 or 1. And if you've had stats 341, you might remember that this is called a Bernoulli distribution. If y takes on 0 or 1 are the two levels that can take. And if you remember from 341, the sum, so we have a bunch of y's in our data set, and the sum of Bernoulli random variables is what we call a binomial random variable. So one method for estimating the parameter pi, the probability, is called maximum likelihood estimation, or MLE. And what we're going to do is treat the likelihood function, what we call the likelihood function, as a function of pi, as a function of our parameter. And we're going to, the idea behind this is we're going to find a value of pi that maximizes, hence the word maximum, that maximizes our likelihood based on the observed value of our data. And the data in this case is just the sum of our y's, or the number of survivors in our data set. So how can I find the value of y that maximizes that expression? We're going to use calculus. To find the maximum of a function, we're going to take a derivative, set it equal to 0, and solve. Is the general idea. Okay. And we're going to work with the log likelihood. It's generally easier to work with the log likelihood because the likelihood is a product of terms. The log likelihood then will be a sum of terms. So it's going to be easier to take a derivative of the sum than it would be to take the derivative of a product. So we don't have to use the product rule over and over again. But it's convenient that the value of pi that maximizes the log likelihood is actually the same value that would maximize the likelihood function. And I'm not going to prove that, but the log function is a one-to-one function, one-to-one transformation. So it turns out that whatever maximizes the log likelihood also maximizes the likelihood. So, and I'm not, some of this I'm not going to give you a lot of details for, but if we're dealing with a binomial random variable, and I write the likelihood function as a function of pi, the probability that y equals 1, then I can write that out as pi to the y, 1 minus pi to the n is our sample size, minus y, where remember here, y is the sum of our 0, 1 y. So y here is just the number of total survivors in our data set, n is the total sample size of our data set. And if you know about the binomial distribution, you'll notice that I'm leaving out, there's a multiplication here, or a factor that's multiplied, n choose y, but that's not going to play any role when we take the derivative, so I'm just leaving that out of my likelihood function. So if I convert this to the log actually, let me write like this. The log of L of pi. So the log likelihood. this requires you to remember something about how logs work, but pi to the y, if I take the log of that, that would be y times the log, the natural log of pi. Similarly, we can bring this exponent down, plus n minus y times the natural log of 1 minus pi. Remember, again here, y is equal to the sum over I of my big y's, the 0, 1 y's. So y here, I'm just calling my total number of successes. And so what value then will maximize this expression? Just to write it out here again, I'm going to say the log of L of pi, again, is y log of pi plus n minus y. So this is the number of survivors. This is the number of people who died, n minus y, log of 1 minus pi. Pi is the probability of survival, so 1 minus pi is the probability of non-survival. So you can sort of see how this is working out. The number of survivors times the log of the probability of survival. The number of non-survivors times the log of the probability of non-survival. So how do we do this? We're going to take a derivative of the log likelihood function. So I'm going to take a derivative with respect to pi. That's our only parameter in this model. And derivative of the log, I'm taking it with respect to pi, so the derivative of the log is just 1 over pi. So this would be y over pi. So we're getting into some calculus here. Derivative of the log of 1 minus pi, we have to use the chain rule for that. But you can say n minus y over 1 minus pi. But then we also get a minus 1 here from the chain rule. So we can simplify this as y over pi minus n minus y over 1 minus pi. That's our derivative, and if we set this equal to 0, we can now solve for pi. So I'm going to solve that for pi. And this is algebra, right? Y over pi equals n minus y over 1 minus pi, which means, this is an arrow, sorry about that, which means that y times 1 minus pi equals n minus y times pi. Take that another step and say y, get the y's on the same side, or I'm sorry, I'm just going to, at this point, expand out everything, right? Y minus y times pi equals n minus y times pi. I'm trying to solve for pi. So then I can say that y equals n minus y plus y times pi. So I just brought those over, I brought the pi's to the same side. Okay. Which means that pi equals y over n. Now, I can stick a hat on there because, and this is also my p hat, this is my maximum likelihood estimator. So the maximum likelihood estimator for the proportion or the probability of surviving is the number of survivors divided by the total sample size. So that's interesting. The sample proportion is the maximum likelihood estimator for the probability. That makes some sense, right? So now, let's calculate the log likelihood at the observed value of p hat for these data. So to do that, I'm just going to recall that in our data set, there were 45 observations and y equals 20 survived. And I'm not sure that I ever actually showed you that. But if I put the data into SAS, so if I run this, and notice I'm not using a freak statement here because I'm entering raw data. Here's the response profile table. So this data set has 45 observations, 25 died and 20 survived. So that is where I'm getting this. 20 survived. So the log of L at p hat is y log p hat plus n minus y times log of 1 minus p hat. We can plug in the values that we have here. So we have 20 survived times the log of 20 over 45 plus, that means that 25 did not survive in our data set, times the log of 1 minus 20 over 45. And if you calculate that out, you'll get negative 30.91. Okay. What is negative 2 multiplied by the log likelihood that we just computed? So let's take negative 2. What I'm asking is negative 2 log likelihood at p hat. And that's just negative 2 times negative 30.91 equals 61.83. And does that number look familiar? Let's see. What did we just calculate? 61.83 is minus 2 times the log likelihood in a model that has the intercept only. So you might have noticed that in my calculations here, I didn't do anything with in my calculations, I didn't consider any covariates at all. So this is similar to a model, or this is equivalent to a model that includes the intercept only. Okay? And if I were going to include the covariates in the model, it would be a little bit more complicated. So this is, in the SAS output, it's labeled as minus 2 log L minus 2 log L, log likelihood, for intercept only model. Okay. And then once we define a model using age and sex, we can do maximum likelihood estimation in the same way. It's a little bit more complicated than what I just did. And so I'm going to stop this video here. This was my math interlude. Okay. And now I'm going to go back to regular programming.